So we'll start with a brief recap of the first lecture. We discussed what a typical personal computer looks like. It has a motherboard with the CPU on it. The CPU is cooled by a fan. The CPU is connected by a lot of wires to a very fast electronic random access memory. And there are also connectors for a bunch of cables that go to a hard disk. Memory and the hard disk are modeled as a giant two-dimensional array of bits. It's 8 bits across, that's called a byte, and as many rows as you can afford. And the logical model of a CPU has an arithmetic and logic unit with a bunch of registers which are connected by the address and data bus to the main memory. At the moment, we are not thinking about disks very consciously, and we model the input and output devices as just specially mapped regions of RAM that you can read and write to interact with the outside world. The rules of the game are that you can fetch a memory location into a register, you can operate on 2 or more registers and save the value into a register, and then you can push the value of a register into some other location of RAM. At the very lowest level, that is the language in which you program computers. Movement of data between registers and RAM and operating on registers inside the arithmetic and logic unit. But that is very tedious to code in, so we started looking at high-level languages where there are high-level statements with variable names which are abstract and symbolic that you can remember and understand easily. And then statements which assign values to those variables which compute values in high-level arithmetic expressions. And then we started slowly getting into the concrete syntax of C++, how to include the I/O library, how to print things to the screen, how to read things from the keyboard, and so on. So that was the first lecture. And in the first week of labs, we looked at how to edit a C++ source code file, save it to disk, compile it using the G++ compiler, and to run it from what's called the command line of bash, which is a shell which runs on top of the operating system itself. So that was the first lecture. Today, we will continue with a discussion of the basic data types which are implemented on top of the very low-level bit array memory that the hardware provides. So we'll discuss what are various types, basic types supported by the language, how to declare variables that belong to those types, why declare at all, how to write down arithmetic logical expressions, and then how to assign those expressions to the variables. Before we get into the business, a few announcements. If you fail to use the attendance machines on the sides of this hall, then please write down your name on a piece of paper and give it to either me or any TA who may be around in the lecture. We will process those attendances manually later on. All lab batches should be stable now. They're linked from the static web page for the site. So click through to Google Docs, search for your roll number and name, verify that the name and roll number are correct, and then check which evening you should come to lab. Your lab batch also defines, in part, the junior TA who is assigned to you. So your first line of defense, in case you are in trouble, don't understand something, would like to go to a makeup lab, whatever, is to talk to your personally assigned junior TA. And if you cannot settle or resolve things with the JTA, then you escalate to the senior TA and then to me. Labs this week will continue with familiarization and small programs. In particular, we'll look at handling command line arguments. So when you say move file 1 to file 2, file 1 and file 2 are called command line arguments to the program called move. So when you write your own programs, you accept those inputs from the outside world through these two variables that are passed into main. So that's one of the things you'll learn. Then we'll write some logical expressions, like Boolean expressions that we'll discuss today. And you'll see that sometimes surprising things happen because of finite precision in the computers. There will be no tutorials this week either, but we will begin posting homework that you can work out on paper on Moodle. You should see them by the end of tomorrow. And this will give you an impression of exam questions, but it will also help you understand the lectures better. These will not be graded, but you should do them regularly. And these problems will be discussed in the tutorials of the following week. So when we start tutorials next week onwards, we'll discuss problems set out in this week. Okay, so as I was saying, the computer memory is measured in units of storage that are bits, which are zeros and ones. And the reason for not choosing a number system with a larger number of distinct values, like the decimal system with 10 values, is that electronically it's easier to build circuits that distinguish between two voltage levels. And if you try to represent 10 voltage levels or even more, then noise may affect the circuits worse than if you just use two levels. Now, these bits are collected into units called bytes, which are 8 bits wide. So if you write down 8 bits, each of which is 0 or 1 side by side, then they can go from all these values, which is all zeros to start with. Okay, now in decimal, what happens, you start with 0, then you increment it by 1, and then you increment it by 2 until you hit 9, after which you cannot increment anymore and you carry over to 10, right? So in binary, the next number is by incrementing this bit, which then becomes a 1, the rest are still zeros. But right in the next step, there is a carryover because there are no more digits left. So the next number is 10, that corresponds to 2. So this is decimal, this is binary. Okay. And if you keep doing these flips, each bit, there are two possible values. There are 8 bits. So the last value you see here is all ones. And that corresponds to the number 255. Okay. And that's because the first position, the rightmost position or the least significant bit is worth 1. The next bit is worth 2. The next bit is worth 4. Until this bit is worth 128. So just like in decimal, the worth of this position is 1, the worth of that position is 10, and so on. Here, the worth increases in powers of 2 rather than powers of 10. Okay. So this would be the case if we wanted to count strictly positive or non-negative numbers. So 2 to the power 8 or 256 possible bit configurations. And if we choose to, we can interpret them as integers between 0 and 255, which in C and C++ is called the type unsigned character. Unsigned meaning it doesn't have a sign. It can't be plus or minus. It's only plus. Okay. So in ordinary computers, all electronic and magnetic memory is allocated in units of bytes. English-based or Western character sets are such that 256 values are typically enough to encode all the standard characters in the typed language. And that's one of the reasons why unsigned character is not called like unsigned byte. Although in Java, there is a distinction between a byte and a character, because in Java, characters can be multiple bytes because it has to support many languages from around the world. Sometimes people write down a byte as consisting of what are called 2 nibbles. So if you write byte as biting off something, nibbling is like nibbling half of it. Okay. So that's called a nibble. And to ease our writing through this lecture, we will talk about 4 bits because we can look at the 16 possible values more easily. Okay. Now, so a nibble ranges between 0 and 15. 15 is the last value. And a nibble is usually written in hexadecimal. Okay. Hexadecimal is just a number system which starts at 0 and ends at 15, except that we don't want to write it in decimal because it takes 2 characters. So after 9, instead of writing 10, we write A, B, C, D, E, F. That is 1 hexadecimal digit. So in other words, a byte value written in hexadecimal can range from 00 through FF. So with a little practice, you can get conversant doing arithmetic in hexadecimal. And a typical hexadecimal number may look like 0A or C5. Okay? So Initially, we might need to write down the correspondence explicitly because it's not easy to remember this. So up to 9 is standard, A is 10, B is 11, C is 12, D is 13, E is 14, F is 15. Okay. So in this system, if I write 0A, that number corresponds to just 10. That is 0A. 0A hex is equal to 10 decimal. And what is C5? C5 is C times 16 plus 5. Okay. And C being 12, this is 12 times 16 plus 5. So C5 in hex is equal to 12 times 16 plus 5 decimal. Well, so if I write down the number 23 in decimal, what do I mean? I mean 2 into 10 plus 3. Now the base has become 16 in hexadecimal digits. So that's how you should read hexadecimal numbers. Now, unfortunately, there may be some ambiguity about whether 23 is 23 in decimal or 23 in hexadecimal. So if you're writing down literal strings in your code in C or C++ or Java, to make clear whether you mean hexadecimal or decimal, in case of hexadecimal, you have to write it as 0x23. That tells the compiler that you mean 23 in hexadecimal and not decimal. If you write only 23, that's decimal 23. So let me give a quick demo to show you how this works. This also shows you a C library called Stdio. Although C++ also provides comparable libraries, some programmers often find it more convenient to use a couple of C libraries for reading and writing values from the screen and to the screen and from the keyboard. So here is one example. So I'll comment out a bunch of things, and so let's say int a equals 0x. What did I have here? C5, right? C5, and now I'm going to just print a and see what that comes out to. I'm going to comment that part. So if I now compile, so it prints 197. Does that look correct? So this is 192 plus 5. Okay. That's 197. But suppose you wanted to print in hexadecimal format, which you often want to do for system programming. The right way to do it is to write printf, print formatted, and then you give two things. One is called the formatting string, and the other is the value itself. In the formatting string, I will say that the next thing to print is a itself, and you say that by saying a %, and then you say %x for hexadecimal, and you say print a new line at the end of it. So this printf statement tells the compiler to produce an output, which is the hexadecimal representation for a followed by new line. If I compile that and run it, we get C5 back again. Okay. Now, I was talking about bytes here, but we have already introduced an int variable. So what is an int variable? In RAM, looking at RAM as an endless sequence of bytes, here is one particular byte with 8 bits. Here is the next byte, again with 8 bits. You could either think of this byte as a byte or unsigned character variable having 8 bits, or you could think of 4 consecutive bytes as a 32-bit integer. Okay? And that gives you more bits and more combinations. We'll soon see how many combinations we can get. And therefore, a 32-bit integer has 4 bytes, or it has 8 nibbles. In other words, it has 8 hexadecimal digits. Okay. So all standard integers in C and C++, which are 32 bits wide, have a 8 hexadecimal digit representation. So suppose I want to print out to a field width of 8 and print all the leading zeros if necessary. That will help us understand numbers a bit better. So I can say that by saying the field width to print is 8, and in case there are leading zeros, print them also. Okay. So I say percentage 08x and the new line. If I compile that and run it, I get all the leading zeros and then C5. So as I was saying, you get only 256 combinations with a byte, and that's not usually enough for doing most programming. So the language provides integers of a few fixed sizes. Apart from bytes, you can get what are called short integers or short, that are 16 bits wide. So you take 2 bytes consecutively, and that becomes your 16-bit number. And if you go through the same exercise again, you'll obviously see that the number of combinations now, instead of being 2 to the power 8, is 2 to the power 16. And that gives you 65536 combinations. So about 65,500 possible numbers. There's one interesting convention that you need to be aware of. If I'm taking up 2 bytes worth of space for a short number, this is the short data type. There are 2 ways of doing that. If I wrote down the number in standard format where least significant bit is here and most significant bit is there, I'd have 2 bytes. Right? Now, in this packing of the 2 bytes into a short, I can either have the LSB here or I can have the LSB there. In earlier days, there used to be computer architectures which followed either of these conventions. One was called the little endian and the other was called the big endian. Not Indian, but endian. Okay, whether the little byte goes in the end or the big byte goes in the end. Now, you need to be careful about this only if you are transmitting data between 2 computers having incompatible architectures. And you are doing that in a low-level data format, then you need to worry about this. But modern languages like Java have taken this problem away because they have a standard encoding mechanism across architectures. Now, even 65536 possible values may not be enough to cover all your programming needs. You may well have arrays with millions of entries in it, so 65,000 is nothing. So the next size of integer that's provided is 4 bytes, that's the standard integer, which is 32 bits. That gives you about 4.3 billion distinct values, and that's adequate for most programming purposes, including indexing arrays and all kinds of things. Except that there are these large amount things, like if you're writing code for, say, I don't know, astronomy or finance particularly, then it's not enough to have 4 billion as the maximum possible number. In which case, you might want to use what are called long integers or longs, which are 64 bits wide. So it's 8 bytes, one after the other, all packed into or unraveled into a 64-bit number. Okay, 8 times 8 bits. Now, these are all what are called fixed size integer types, and they count up in discrete steps. All their 2 to the power bit values can be equally used. But they are not enough for scientific applications where you have to represent really astronomical distances, literally, distance between Sun and Pluto and other stars and so on, for which we need scientific notation. So it's like 6.5 into 10 to the power 23. So how do we represent those? Those are done using what are called floating point and double precision floating point numbers. Okay. Whereas byte, short, int, long, character, those are all called fixed point numbers. Now, before we get into floating point numbers, let's finish off most of what we have to do with fixed point numbers. So we saw that in case of a 4-bit number, we can choose to represent only non-negative numbers between 0 and 15. But obviously that's not adequate. Even if you're writing a banking application, you might want to represent debits and credits with signs, and you might want to cancel off debts by payments and so on. So you need both positive and negative numbers. Now, a very simple way to represent positive and negative numbers is to set aside one of the bits as a sign bit. Right? So suppose I was given 4-bit position. I say this is going to be my sign bit, which can be either 0 or 1. 0 might mean positive, 1 might mean negative, say. And then these 3 bits can go through 8 combinations. 0, 0, 0 through 1, 1, 1. So this is decimal 0. This is decimal 7. So now, instead of getting only positive numbers between 0 and 15, I get both positive and negative numbers between 0 and plus minus 7. Okay? But note that 0 has a precarious position because 0 can be written 2 ways, either as plus 0 or as minus 0. Right? And so now I have 0 through plus 7, minus 0 through minus 7. I thought those were 16 distinct values, but actually I've lost 1, so I get 15 distinct values. And besides, anywhere you're doing an arithmetic comparison between 2 variables, one of them might have been set to plus 0, the other one might have been set to minus 0. They're actually the same thing. So if you have these comparator circuits which ask if they're equal, they have to be designed specially for one number. That's ugly. Besides, we are losing one possible value. Right? So what is the remedy? The remedy is to use what's called 2's complement arithmetic, which goes as follows. We want to represent both positive and negative numbers with this bit sequences, say 4 bits. And so what we do is we do the same thing as before for the positive guys. Okay. So we say that as long as the first bit is 0, that constitutes my set of positive numbers. Okay. So although it's a little tedious, I'll write down the whole set because it'll be easier to look at them in future. So I start at 0. Okay, so this is 0 decimal, that's 1 decimal. So that's the positive numbers. Okay. And then I have 8 more values left, right? I have exhausted 8 values in the non-negative numbers. So I have 8 more values left. So what I do is we assign them between minus 8 through 1. And we do it in a particular way. We basically say if I clocked this up 1 more, I would get 1, 0, 0, 0, right? I'll actually stick that right at the top, 1, 0, 0, 0, and call it minus 8. Then I increase it again. Then I'll get that. And I'll increase this also by 1. So that's minus 7. Okay. So 1, 0, 1, 0 will be minus 6. 1, 0, 1, 1 will be minus 5. 1, 1, 0, 0 will be minus 4. And all ones will be minus 1. Okay. Now this looks like an arbitrary design choice, but it's actually very well considered and it has a lot of nice properties. Now the first thing that might jar you a little bit is that in the positive number world, it felt very natural to go from 0, 1, 1, 1 to the next number, and I should have really kept on going positive. This looks like a sudden jump from the highest possible positive value represented to the lowest possible or negative value represented, right? Whereas earlier my sense of a wraparound was here. That's when the clock rolled over and I started again from the beginning. But now this has become a much more natural transition from minus 1 to 0. Whereas something that looked like a more natural transition from 0, 1, 1, 1 to 1, 0, 0, 0 has now become a jump from the highest positive to the largest magnitude negative value. Okay. So this is called 2's complement representation. You can see the chart also here for only the negative values. So the wraparound happens from the maximum value, which in binary looks like a 0 followed by all 1s, to the most negative value, which is 1 followed by all 0s. And then minus 1 in this 2's complement system is always all 1s, and 0 is always all 0s. Now, this has many, many important properties, so I'll just tell you one, which is, suppose I take the number, say, 5, which is 0, 1, 0, 1. Let me complement each bit. If I do that, I get 1, 0, 1, 0. Let me add 1 to it. I get 1, 0, 1, 1, which is minus 5. So that's why it's called 2's complement. You can take a number, you can negate all the bits. That doesn't directly give you the negative of the number. To get the negative, you add binary 1. Okay, that's how you negate a number. Now, let's verify that if you add a number and its negation, you get 0. You should do that, right? So, minus 5 was 1, 0, 1, 1, plus 5 was 0, 1, 0, 1. If I add them up, 1 plus 1 is 0, carry over 1. 1 plus 1 is 0, carry over 1, carry over 1. And the rest overflows. You forget that. Okay. In finite precision arithmetic, if a carryover bit is found, it's just thrown away silently. You never know about it. So just like in decimal, if I say 64 plus 26, what happens if you add 4 and 6? You get 10. That overflows the last number 9. So you do a carryover here, right? So in binary, there are only 2 possible values. If they add up to 2, you can't write down 2 here. So go to 0 and then you carry over 1. So that's 2's complement arithmetic. It has certain other interesting properties that we'll explore in the tutorial. So there's one sudden wraparound from 7 to minus 8 in case of one nibble, 4 bits. Now, this works exactly the same way for short, int, and long ints with their corresponding wraparound point, maximum value, and minimum value. Okay? So, observe that if I wrote down the number line, 0 is, so there is a equal number of configurations with a 1 in the leftmost position and 0 in the leftmost position, right? One of them is 0, and that's a little asymmetric because it's the first value to be used on the positive side or non-negative side. Okay? And then strictly positive numbers, you get 1 fewer than strictly negative numbers. 0 is included on the positive side, or so-called, side with zeros on the first significant bit. And when you wrap around from large positive values to large negative values, the system will not detect it, you will not get any warning, there will be no exceptions thrown. So if your program necessarily uses values which are close to the positive or negative edge of the universe, you need to be very careful in doing arithmetic and checking for the results to make sure that unintended things are not happening. I'll give one example of that. Now if you are unhappy with fixed precision integers as provided by the hardware, you can always fake it in software. We'll see that in later labs. There is no reason to say that my integers have to be all of a fixed size of 4 or 8 bytes. If you have the space in your RAM, you should be able to represent arbitrary precision integers. And there are libraries for that. You can write your own with a little effort. But because that is supported in hardware, operations on such integers will take much, much longer than fixed precision integers, which can be processed in a few cycles. So typically today, CPUs have a certain clock speed. When you buy a CPU, it will say 2.5 gigahertz or 2 gigahertz. So one cycle is 1 over that amount of seconds. And 2 integer additions can typically done in at most 2 to 3 cycles. Okay. Whereas if you implement this in software, it will take hundreds of cycles, if not more, to do a single addition. So software arbitrary precision integers are slow, but sometimes you need that because you want exact numbers to be preserved. So let's look at our example code and a few other things. So as I was saying, here's more code. So now I'm going to, well, I can't redeclare int. That the compiler will complain. So I'll comment that one out now. So now I am initializing a to the last or largest possible positive value. Okay. In hexadecimal, the number 7 is 0111. So if we write down a large, int or long in hexadecimal and it's the largest possible positive value, it will always look like 7 followed by f's. F is all ones. And I'll write that down as a decimal. I'll print that out. And I'll also print it out as a hex. And then I'll increase it by 3. You will see that it will result in what looks like a negative number. Okay. So we start off with this largest possible 32-bit integer, whose hex representation is 7 followed by 7 f's. So that's the exact point I made before moving on. We are writing this in hexadecimal bits, base 16. Remember that in base 16, numbers go from 0 to 7, 8, 9, A, B, C, D, E, F. Okay, in hex there are 16 digits. And so if I'm trying to write down the number which is 0, 1, 1, etc., and here is, 8 bits. Okay. The first 4 is a 7. The second 4 is F. And then F for all the others. So I initialize to the largest positive integer. I increment it by 3 and I get a very negative integer. And that's what you see here. Okay. And in hex, though, the thing looks natural enough. The 7 has increased to an 8. 8 is 1000, right? And the rightmost hex digit has become 2 because I added 3. Okay, I added 3 here. So in the lab, you will study this more carefully by writing code and feeding it values of your own. But this is the thing: the C compiler will not bother that by adding a positive number to a positive number, you've gotten a negative number. This is perfectly possible because of finite precision arithmetic. And if you use a long, you're just going to get more mileage, but eventually it is going to wrap around. So one of the first things you need to learn is some amount of defensive coding, so that if your application may drive integer numbers near the edges of the representation, you need to be extra careful to check the values and do the right thing. So as I was saying, there are scientific applications for which integers are not enough, and you do need this floating point number representation for reals. Okay. So in decimal, we write real numbers in scientific notation as a mantissa and some exponent. Okay. So we can write 0.314 into 10 to the power 11. And there are some conventions about how to range the mantissa. For example, there's no point writing 314597 into 10 to the power 5. You would rather keep the mantissa either between 0 and 1 or between 1 and 10. And you can always do that by adjusting the exponent. Right? So in this class, our convention will be that the mantissa is always a fraction, okay, between say 0 and 1/10 in case of decimal and 0 1/2 in case of binary. Okay. In decimal, if we write down a fraction, the assumption is that there is a decimal point at the beginning, and then there are fractional digits. So here is the decimal point, here is the first decimal digit, here is the second decimal digit, here is the third decimal digit, and so on. And the value is what of this thing? It's 0 point there. So it's d1 over 10 plus d2 over 100 plus d3 over 1000 and so on. Right? This is still the most significant digit, and significance decreases as you go to the right, same as before. We have just taken an implicit decimal point in front of all the digits. In binary, if I write dot B1, B2, B3, etc., it's the same. What I mean is that it's B1 over 2 plus B2 over 4 plus B3 over 8 and so on. That's the number. Okay. So suppose we take our 4-bit system here and pretend that we have a dot in front of everyone. Then what kind of fractions can we represent? 0 is still 0. Okay. Now our positional values are half, 1/4, 1/8 and 1/16. Right? So this number is still 0 in decimal or eventually fractions. This number is 1/16. Only the least significant bit is on. And so on, things keep increasing until, since they're all positive, there's no sign yet, this number becomes 15/16. So we don't have sign now, we are really going that way. This is the max and this is the min, which is 0. Okay. So if you want to represent binary fractions, this is how you do it. And the more bits you have here, the finer you cut the space. Instead of values jumping in units of 1/16, if you allocate 8 bits, values will jump in fractions of 1 over 256. Right? And so the more bits you add to the mantissa or the fraction, the finer grained your separation is going to be between adjacent numbers that you can represent. So in computers, when we write floating point numbers, the mechanism is the same. There is a fractional mantissa with a sign, and then there's an integral exponent like 11 here in the decimal case. Okay. There are 2 primary floating point numbers provided in standard computers. One is a 32-bit float and the other is a 64-bit double. In a 32-bit float, 1 bit is allocated for the sign. Okay. There are 8 bits for the exponent, which are represented in 2's complement manner, because the exponent can be both positive and negative. And then the mantissa is a binary fraction, like I've drawn out on the board. Okay. There are 23 mantissa bits and 8 exponent bits and 1 sign bit. In a double, meanwhile, there is the same 1 sign bit, 11 exponent bits and 52 mantissa bits. Why this particular division of bits between exponent and mantissa? That's an industry standard based on applications that people have found compelling. Okay. That's how the architecture has been set up, and all machines now have this exact same floating point and double floating point representation so that you can freely interchange data between machines. There's nothing particularly, cosmic truth about this. If somehow in history it turned out there are 9 exponent bits and 22 mantissa bits, that wouldn't overthrow the universe, but it's just a standard that's been set up. Now if you do the math, so one quick envelope calculation that you should know is that suppose I have a b-bit number, that means you can go up to approximately 2 to the power b. Now, if you want to ask, that's roughly equal to 10 to the power what in decimal? Okay. How many decimal digits do you get if you have b binary bits? Then you say b log 2 equals d log 10. And so d is equal to b times log 2 to the base 10. Okay. Which is approximately equal to 0.3 b. So if I give you 30 bits, you get roughly 9 to 10 bits of digits of decimal representation, about 1/3, so it's less than 1/3. So if you use that and work out all the details, you will see that floats can represent a maximum magnitude of about 3.4 into 10 to the power 38 and a minimum magnitude of 1.4 into 10 to the power minus 45. Okay, you should work it out offline. Based on the representation I've already told you, you can do it. And 64-bit doubles can represent a maximum value of about 1.8 into 10 to the power 308 and a minimum value of 4.9 into 10 to the power minus 324. Now, compared to long integers, this of course looks impressive, but you realize that the number of bits in a long integer and a double are exactly the same. So the number of distinct real numbers that you can represent will also be about the same. There is no free lunch. You get the number of bits. The number of bits decides how many different combinations you get. So in other words, finite number of bits can never represent all real values. Real values on the line are infinitely densely packed, and a finite number of bits only gives you a finite number of dots on the line. So computers cannot represent most real numbers. Computers represent only a vanishingly small fraction of real numbers possible, even within that range. It's measure 0. You cannot represent most real numbers. And this leads to a whole field of computer science. You need care in writing expressions that combine values to avoid errors and to minimize loss of precision. If you are computing a solution of a linear or nonlinear system of equations, you are solving a differential equation numerically. You are computing the eigenvalues of a matrix numerically. You have to take immense care, and there are multiple PhD theses written on it, which do the calculation in a way that maximally exploits the number of bits available in the machine all through the way until the end. Okay? In the sense that you don't lose any precision that you can avoid losing. So that's a really difficult science, highly non-trivial. So let's see some of the effect of this. Apart from having a finite number of bits to represent reals, some bit patterns have to be set aside to represent special values. For example, positive and negative infinity. You can easily go and write, and we will do so, write a C++ program where you divide 5 by 0. Dividing 5 by 0, the answer is plus infinity. Okay. Once a value reaches plus infinity, if you say subtract 100 from it, the answer should still be plus infinity. There is a consistent set of axioms for finite precision arithmetic, which tells you that infinity minus 100 is infinity. But how about infinity divided by infinity? Now you don't know. 0 divided 0 or infinity divided by infinity is indeterminate. That's not a nice expression to carry around. It's not an expression you use to aim a rocket or pour some chemicals. So that's represented by what's called not a number, or nan. Okay? And nan can happen because you divided 0 by 0 or you subtracted infinity from infinity and so on. So if you do those dangerous operations, the bit pattern of the number is set to this illegal value, so that thereafter, if you start trying to use this number in combination with other numbers, it kind of contaminates all of them and everything becomes nan. Okay? Now, most systems will detect overflow and turn things into infinity properly, but most systems will not detect underflow in the following sense. So suppose I have a floating point number a, which is 3.3 into 10 to the power 38. That's very close to the maximum value of 3.4 into 10 to the power 38. And now I divide it by 0.01. Okay? This will correctly result in a being set to the value called inf. Inf is a special bit pattern in float and double numbers that the compiler understands. So even while printing out that value, the runtime library doesn't print a bit pattern, it says it's infinity. But if I take 3.3 in 10 to the power 38 and I add 5 to it, so by the way, this 3.3 E38 is just 3.3 into 10 to the power 38, it's shorthand for that. Now if I add just 5 to it, if you had to do that calculation manually, what would you write? So you have 3.3 into 10 to the power 38 plus 5, which is into 10 to the power 0, right? The first thing you have to do is line up the exponents. Right? So you do that by saying 3, 3, and then you keep adding how many? Approximately 37 zeros, right? That's the first number which has now been denormalized. And then you add the 5 here. So you get 3, 3, followed by 36 zeros, followed by a 5. When you try to normalize that and fit it back into a float, you will realize that given the number of mantissa bits you have, that 5 will drop off the face of the earth. Okay, it will be lost, and your answer will still be 3.3 × 10⁻38. So anytime you add very large and very small numbers whose dynamic range exceeds the number of mantissa bits that are allocated, you run the risk of losing precision, underflowing the smaller number. And normally this may be okay, but there are certain calculations in physics and in computer science where I may actually build up trillions of such terms, each term being very small, added to a large number. So in true infinite precision arithmetic, you will get a much larger value than if you keep adding small numbers to large numbers and losing that precision. So you have to be careful about the order in which you do that arithmetic. So we'll talk about that later when we do a bit more data structure work. How do you finally declare variables as belonging to types? So you say float Fahrenheit. That defines the variable called Fahrenheit to be of type float. So 4 bytes are allocated for it somewhere in RAM. And initially those bytes have no initialization in C and C++. In Java, it's guaranteed to be initialized to 0. But many C and C++ implementations for efficiency will not initialize it. So if you read, you might get garbage. Or you can declare the variable together with an initialization by saying float Fahrenheit equal to 95. Okay. If you know that the value will not be subsequently changed or assigned in your code, you might add a notation called const, which means constant. Here is a floating point value called Fahrenheit, which I'm initializing to that value, which will never change. That has a couple of benefits. First of all, if you by mistake try to assign to that value later, the compiler will catch you and give you a warning or an error. The other advantage is that because it's a constant value, it doesn't need to be loaded from RAM. If I need that value, I can always load the constant into a register without consulting RAM, and that can speed up my code. Okay. Remember that the number of registers is very small. Registers are very fast and they're precious. So when I'm computing large arithmetic expressions, I often need to flush values from registers back to RAM to make space in the registers. If the value is a constant, I don't need to flush it back. I can just forget it. Okay. So for all these reasons, if you can afford to declare a variable as constant, please do so. It will speed up your code a little bit. And finally, you can declare values of variables to depend on other declared values of variables. So you can say int x equal to 3 and y equal to x over 2. And by that, y will use the value of 3. But 3 divided by 2 in integer is 1. It's not 1.5. So when you write integer divided by integer, you mean the lower value. It rounds down. Okay, it takes the floor. So why bother to declare at all? There are languages where you don't need to declare variables. You just pull the variable out of thin air and start using it. Perl is one such language. Now, however, it's really bad to code in languages that don't require you to declare variables, because what if you type it incorrectly later? A single character error in using a variable later on might read garbage for you. So declaring is always a good idea. You should always use languages which make declaration of variables compulsory. And also, you can initialize it before any use. So the compilers can usually catch if you run a risk of using a variable before declaring and initializing it. Why do we need to declare that a variable belongs to a particular type? One important reason is that many assignments to that variable can be checked for safety. If I declare a variable a to be float, and then I say a equals hello world, that's clearly meaningless. And a compiler can catch it. Then the compiler also can interpret the bit sequence representing that variable as intended in your program. If you look at the RAM of a machine, you have no idea where variables start and where they end. They're all amorphous sequence of bits. It's only the compiler's internal tables which maintain the sanity of the binding between your logical variable names and what offset in memory holds that value, and also what type they are. See, both a float and an int are 32 bits. They occupy 4 consecutive bytes in RAM. but they mean completely different things. In fact, the same number 17 written as a floating point number in 4 bytes looks completely different from what 17 looks as an integer in that same 4 bytes. So your bit representations do not carry type information in themselves. The bit patterns in RAM become meaningful only in conjunction with a type. You start having a value which is meaningful only if you say these 4 bytes hold an integer for me, or they hold a float, or part of a character string. Now, as I was saying, there are languages that do not enforce variable name or type declaration, but that's generally a bad idea with a capital B and a capital I. Okay. Never use a language which is not fussy about typing and declaration. So now that we have finished the basic floating point and numeric types, let's go over how to combine these values into expressions. And most of you have, written enormously complicated arithmetic and algebraic expressions, so there's nothing particularly fancy about this. Just a few rules. Multiplication is not implicit as you write down on paper. You say 5x, you have to write 5 times x explicitly, because the computer doesn't know otherwise what to do. So that's the start. And different operators have different precedences. Some operators bind more tightly than others. For example, if you wrote the second expression, 5 star Fahrenheit minus 32 over 9, star and slash bind stronger than minus. This is the binary minus. So the second line here would evaluate as the second expression tree here. First, the variable Fahrenheit would be multiplied by 5. Simultaneously, 32 would be divided by 9, and then the difference would be taken. Whereas, if you wanted the first expression, which is the correct expression for transforming into centigrade, then you would have to provide these brackets so that the ordering of operations is clear. In this case, the first thing that would happen is Fahrenheit minus 32. Then you would multiply it by 5, and finally you would divide by 9. Totally different expression trees. Okay? And there are levels of precedence. Star and slash are at the same level, in which case it goes left to right. So you can consult, there is a link on the resource pages where there is an official C++ specification for operator binding strengths and what is computed before what else, unless you override with brackets. Normally you will learn the rules of the game, the operator precedence game very quickly, but while you are coding, if you are unsure of the relative importance or binding strength of different operators, it's much easier to just put a bracket and forget about it and not worry about it. Okay? Using a bracket will not increase the time taken for your code to run. It will just make it unambiguous to the compiler. So among the first thing a compiler does on encountering expressions like this is to turn what used to be a string in your input file, C++ code, into an internal representation which looks like this tree. So here is another longish expression for the root of a quadratic equation, minus b plus, in this case, plus square root b squared minus 4ac over 2a, and that's the corresponding expression tree. So the compiler scans your source code file, and it internally turns it into this expression tree, where you compute b squared, you compute 4 times a times c, you take the difference, you invoke a function, we'll learn about that soon. Then you say b, and this is a unary minus, this is not a binary operator, this is a unary operator, that actually binds stronger than plus. Okay? So you first negate b, then you add b to that square root, meanwhile you do twice a, and then finally you divide it. Okay? Now once that expression tree is built, now the compiler needs to worry about how to use that finite number of precious registers it has to pull values, compute internal nodes in the tree. If you run out of registers, how to push it back into memory, okay? And to plan that so that the movement of data between the registers and the memory is minimized. Use a small number of registers, minimize movement of data between registers and RAM, schedule the operations so that if I need a value from memory, I'll want to issue that fetch sometime in advance so that I can do more register computations in the meantime as the value is arriving from memory. Because as I said in the first lecture, main memory is much slower than register to register operations. So all those optimizations are the subject of compiler design and code optimization in computer science. Okay. Here we are just customers to all that technology. Finally, once you compute that expression, you have to assign it to variables, and that's pretty easy. You just say LHS or left hand side equals right hand side. except that the left hand side has to be a variable name. You cannot assign to 5, that doesn't have any meaning. Later on, when we consider arrays and pointers, the left hand side will not be a simple variable name, it can be other things. We'll see that in due course. The right hand side has to be an expression which is compatible with the type of the left hand side. It doesn't need to be the same as the left hand side, it has to be compatible. For example, the right hand side may compute the integer 5 and then assign it to a floating point number. Or it can compute the floating point value 17.3 and assign it to a float or a double, because a double can represent a broader space of numbers than floats, which can represent a broader set of numbers than integers. And the assignment statement itself has a value, which is the same value as was assigned from the right hand side to the left hand side. And this lets you cascade assignment. So you can say x equal to y equal to z plus 1. So both x and y get the same value in this case. There are exceptions to this. When we come to expression operators, we'll look at that. Now, C and C++ unfortunately allow some legacy abuse. For example, you could say x equals y greater than z. Okay, what does that even mean? So this second greater than is a test. It compares y and z, and if y is larger than z, then the value of this expression is 1, otherwise it is 0. So logical or Boolean values are collapsed into integers, except that false is 0 and true is 1, or maybe any other non-zero value. And that's a problem, it's a bug, it's not a feature. So now let's look at some simple code to do some operations. For example, I have two floating point numbers, 5 and 11 in x and y, and I want to swap them. So I declared a temporary variable called temporary, which I assign to x, and then I assign x to y, and then y to temporary. And as a time trace, I start up with 5 and 11, temporary doesn't exist yet, and then temporary is assigned to x, so temporary becomes 5, y remains 11. In the next state, x equals y, so x becomes 11, y is also 11, temporary is 5, and finally y is assigned to temporary, and so changes from 11 to 5. So at this point, the values have been swapped. So some of you may already know or can figure out how to swap the values without using a temporary variable at all. Okay. So see if you can figure that out. If so, mail it to us and we'll comment on it. There is one well-known solution, but you need to think a little hard about whether it works under all situations. Okay. The next kind of expressions we will consider will be logical or Boolean expressions. And as I was saying, these are 0, 1 or true false values, which are the results of various checks or comparison between numbers and so on. So for example, 5 less than 13 is a Boolean expression with value true. In C and C++, that true is represented by some integer which is not 0, typically 1, but not necessarily. 1e5 greater than or equal to 2e6 is a Boolean expression with value false or 0. Okay. If you want to test for equality, that is different from assignment. Assignment is just single equal, whereas test for equality needs some other symbol, so that's 2 equals side by side without a space. Okay. Now, in the days before integrated programming environments, a very common bug in C or C++ code used to be using equal to when you mean equal and otherwise. So it's very easy to create a typo or a typing mistake where you mean equal but you type equal. That's more easy to catch because no assignment is happening. Much more dangerous is if you are testing for equality but end up assigning instead. Because the assignment operator also has a value, it's very dangerous to replace a double equal by a equal. Some invisible assignment happens and you never know. Some programmers get into the habit of putting the literal constant on the left hand side of an equal to, so that if they miss the double equals, you're apparently assigning to the literal 5, which the compiler will flag. If you put a variable on the left hand side, you can always assign. Okay. So, in case you are spacing out there, if you're comparing, if 5 equal to x, do something, and somehow you miss this equal, that's a meaningless statement, and the compiler will complain. Whereas if you say if x equal to 5, do something, okay, that's a bug which will not be caught by many compilers. Okay. It will actually assign 5 to x. the value of the assignment will be 5, which is not equal to 0. Therefore, it will be considered as true, and this will be executed. Whatever follows here will be executed. And x would have been clobbered in the meantime. So be very careful with equals and equals equals. And then just like complicated arithmetic expressions, you can also build up complicated Boolean expressions by combining things. So here is a combination expression by first comparing a with b plus 1 and c not equal to d or not e less than equal to f. Okay. So this is the corresponding expression tree for that expression. So just like in arithmetic expressions, there is a precedence ordering between Boolean operators. If I have bracketed, the meaning is clear. So one of the tests is a equal to b plus 1. Of course, underneath b and plus 1 have to be combined and so on. So the full expression tree is a hybrid between Boolean and arithmetic expressions. So here is a placeholder which is plus b1. Up to this is an arithmetic expression, then this becomes a Boolean expression. So I'm testing if a is equal to b plus 1. So b and 1 have to be combined through an arithmetic operator called plus. That gives me a value which is nameless. That is compared with a. The result is a true false value which goes up. So think of the expression tree as collecting primitive values at the leaves and then passing on more complicated expressions up the tree. Okay. The next thing I do is, okay, so there's a choice between and or, and binds stronger than or. So and will happen first. So now I'm comparing C and D to see if they're not equal. That's another Boolean expression, okay? That is a logical operator. This is an arithmetic operator. That's a logical operator. Now these two come into the node called AND, which is represented as AND. Okay, so, and then here is E less than equal to F. That's a Boolean operator. And then I take these two and then I OR them together. Okay. So in human language, this is logical OR. This is AND. So this is a logical operator, right? So how about Boolean algebra itself? So Boolean algebra itself, most of you are familiar with it, at least. So there are true or false values. So in the world of zeros and ones, false and true. And there are rules of the game. So if I am negating a Boolean value, if input is 0, output is 1, input is 1, output is 0. If I am ANDing together two Boolean variables, then the output is 1 only if both the inputs are 1. If I am ORing two variables together, then the output is 1 if any one of them or both of them is 1. Okay. So there are many Boolean operators, the main ones being NOT, OR, AND, and sometimes XOR. XOR is exclusive OR, which means that if both of them is off, then the output is off. If both of them are on, the output is off. If one is on and the other is off, then the output is 1. That's XOR. So mainly these four Boolean operators cover everything you want, and those are expressed in C and C++ as the single ampersand, the single bar, and the XOR is the caret operator. Okay. So there was this expression of, so this was 1, and so here is E and here is F. I am computing if E is less than equal to F, and then I am negating it. Okay. So not of a condition is what it means. If the condition is true, then the not is false. If the condition is false, then the not is true. Okay. Now, of course, this is much more easily represented as E greater than F, simpler to type. There's another example, which is you can write not E equal to F, or you could write E not equal to F. So there are a few ways of writing the same logical expression. Okay, use whatever is convenient in the code. So that's what I mean. Is that clear? Okay. So as I was saying, in C, you are allowed to write something like if 5 then stuff. Okay. Of course, if 5 means nothing, okay, it's rubbish, but C allows this by interpreting anything that's not 0 as true. If you say if 0, that's 0 is false. But if you say if 5, that will execute. Okay. So this is a dangerous legacy, and so you should try to avoid it like the plague. So don't depend on C or C++ using an integer as a Boolean value. Okay, make sure you understand what's going on. This is especially troublesome in case you get the precedence order wrong, don't put brackets at the right place, and you actually get an integer where you're expecting a Boolean or vice versa. So check your expressions very carefully for that. So let's see if I have a few sample codes to show you. So let's look at float. So here's an example. I start with a very large positive value, okay, and then I add 100 to it, and I print it out. And then I take the similar positive value and I divide it by a very small number that should overflow. So we will check what happens if we overflow. Finally, I'll take b equals a minus 100, I'll print b, and then I'll multiply b by minus 2 and print it. So let's see what should happen. Z is very large, 100 should underflow, you shouldn't see that, so Z should print out to be exactly almost this value. And then A should overflow and become infinity, B should be infinity minus 100, which is infinity. And then by multiplying infinity with minus 2, I should get minus infinity. Okay? And finally, I will take A, which is supposed to be infinity, and divide it by minus infinity and see what happens to that. Okay? I will also write A minus C, which is infinity minus minus infinity, and see what happens. So let's compile this and run that. So in the first case, I print out Z, which is the same as the first value here. So the 100 dropped off. 100 was nowhere to be seen. In the second case, I divide that large value by 100 and that overflows to infinity. In the third case, I subtract 100 from infinity and I still get infinity. In the fourth case, I multiply infinity by minus 2 and I get minus infinity. Then I divide infinity by minus infinity and I get nan with a minus sign which you may not care about. And finally, I take infinity and subtract minus infinity and I still get infinity. So that's because it's infinity minus minus infinity, okay? If I took A plus C, let's see what happens then. Then we should get nan, but who knows? Okay? That's nan. Right? So that's how floating point numbers work. Okay, so it's 12:21, and this time you can get really noisy as if you haven't done enough. We'll start with characters next time.